Hello and welcome to day 3 of Unit 4. Today we're going to take things that we've talked about from the first 2 days and put them together and really put them to use. So we're going to be graphing functions. We're going to start with a rational function, then we're going to look at a few other really kind of interesting functions, some things that you may or may not have seen. Graphing rational functions is something that you've done in pre-calc, I think, but definitely in Algebra 2, and especially in Algebra 2 Honors, you graphed rational functions that were really interesting looking. But what we're going to use is the knowledge that we know about first derivatives and second derivatives combined with things like x-intercepts, y-intercepts, asymptotes, vertical asymptotes, horizontal asymptotes, domains, and in behavior to come up with a full picture of what these functions should look like when graphed. Okay. So the other thing is, since there is so much information per example, do mind that I will be using some notes today that I've written ahead of time. So if you see me looking down, that's me looking at the problems that I've already completed. Okay. So to start, we're going to start with this rational function here. It looks fairly, it's fairly friendly, right? And the first things that we want to do is we want to think about what is the domain of this function, okay? Because that's going to help us start to formulate what this graph looks like. And this function is defined for all real numbers such that x is not equal to plus or minus 4. Okay? And that comes from the fact that the denominator when x is 4 or negative 4 becomes 0. Okay? We want to look at intercepts, at the x-intercept. Well, the x-intercept is what I get when I let y equals 0. And if y is equal to 0, that means that the numerator there has to be 0, giving us a an x-intercept of x equaling plus or minus 2. Now, I'm sure your pre-calc teacher would tell you that an intercept is a point, right? So it's plus or minus 2, comma 0. Now my y-intercepts, my y-intercepts are what I get when I let x equal 0, which leaves me with negative 8 over 6, negative 16, or positive 1/2. And remember, an intercept is a point. All right. Knowing whether this function is odd or even, that might help as well. So what happens when I plug in negative x? When I plug in negative x, because everything is squared, I get back f of x, okay? Which implies that this function is even. Okay? Asymptotes. All right. Well, the domain tells me something about some vertical asymptotes. Let's say at x equals plus or minus 4. And I have a horizontal asymptote at y equals 2. Horizontal asymptote, y equals 2. Degrees are the same. Okay. All right, now we want to go into first and second derivative tests. This is when things will start to get a little bit messy, because to do the first derivative here, this isn't L'Hopital's rule. I actually have to do the quotient rule. Okay? So bottom times the derivative of the top minus the top times the derivative of the bottom, all over the bottom squared. Okay? Now, I'm going to take some liberty and simplify this real quickly down to negative 48x over, x squared minus 16 squared. Okay? And the first derivative test says we want to know where that's equal to 0. Okay? That's going to be equal to 0 when x is equal to 0. So I have a critical point at 0, but I also have to take into account asymptotes. Okay? Stationary points are anything that are critical points or asymptotes, any kind of break in discontinuity. Okay? So my asymptotes, vertical asymptotes, were 4 and negative 4. So I also have 4 and negative 4. And those were vertical asymptotes. Okay? The VH just to distinguish between the fact that this is a critical point and these were vertical asymptotes. Now, excuse me. Okay, I have to test points in between all of these stationary points. Okay, let's test 1, negative 1, 5, and negative 5. Okay, well, when we plug in 5 to my first derivative, the top is negative, and the bottom is always positive. Negative divided by positive is negative, so this is decreasing. When I plug in a 1, the top is negative, the bottom is always positive because of the square. So this becomes negative again. Hey, when I plug in negative 1, I get a positive on top, and the bottom's always positive, so this is now a rising slope. And the same thing happens when I plug in negative 5. Don't forget to label that this is your first derivative test here. Okay. So now I have an idea about increase and decrease. The last thing I need to know is what's going on with my second derivative. Now again, I'm going to take some liberties due to board space and time, and give you that the second derivative does come out to be 144x squared plus 768 divided by x squared minus 16 cubed. Okay. And now that is equal to 0. Never. The top will never be 0. Therefore, f double prime of 0 can never be 0. So 0 is not a stationary point. 0 is not something that I'm interested in. 0 is not a possible point of inflection. However, I do need to take into account the vertical asymptotes. So still 4 and negative 4. So I'm going to try 0. I'm going to try 5, and I'm going to try negative 5. Okay. Well, when I plug in 0, the bottom is negative, and the top is positive. So I get concave down. When I plug in a 5, positive 5, the top is going to be positive. It's always positive. And the bottom is going to be positive because 5 squared is larger than 16. So I get a positive number cubed, which gives me a positive divided by a positive, which is positive. So I'm concave up. Okay. And the same thing is going to happen with the negative 5. When I plug in negative 5 to the top, the negative 5 gets squared, becomes positive. The top is now positive. The bottom, negative 5 squared, is a positive number that's larger than 16. So I have a positive number cubed. Positive divided by positive is positive. Therefore, I'm concave up. Now let's try to graph this thing. We have all the information we need. We know my domain is all real numbers except -4 and 4. So something's going on at -4 and something's going on at +4. Okay. I have vertical asymptotes there. Okay. I have x and y intercepts. I have x-intercepts at + and -2. I have a y-intercept of 1/2. If that's 1, then that's 1/2. Okay. It's even. So it's symmetric about the y-axis. So if I can get that side of the graph graphed, then I've got that side of the graph graphed. Right? In fact, since I know that the function's even, when I did my first and second derivative tests, I really only needed to do that side, because the other side's got to be the same. But I did the whole thing anyway. Alright, so first derivative, and I have a horizontal asymptote at 2. So that's 1, that's 2. Alright, now let's graph this guy as something pretty, like green. Green's nice. From -4 to 4, I'm concave down. However, from -4 to 0, I'm increasing. And from 0 to 4, I'm decreasing. Right, increasing from -4 to 0, and decreasing from 0 to +4. However, between -4 and 4, I'm concave down. Okay. Now outside of 4, on that side of 4, I'm decreasing and concave up. And decreasing and concave up looks like this. And on this side, remember I'm even, so I've got to be symmetric. I've got to look the same. So there's the graph of my function. And it's fairly accurate too. It's fairly accurate. Okay. Okay, so for the next example, something a little bit stranger. Maybe you know what this kind of function looks like already, and you can sort of think about what it might look like. But for those of you who don't, we're going to take a look. And this is going to be the first time you really graph something that's kind of bizarre. Something you haven't really seen before. So again, excuse me if I'm looking at my notes, but there's a lot of information to get down, and I want to make sure that I get it down right. Okay. So the first thing we're going to do is we're going to want to look for the domain. What's my domain? In this case, it's all real numbers. So all the real numbers. But you might be thinking, Mr. Southern, you can't take the square root of a negative number. Well, that's true, but I'm not taking the square root, I'm taking the cube root. And I can take the cube root of a negative number. And in fact, since I'm squaring it first, I'm never really taking the cube root of a negative number in the first place. I'm always taking the cube root of a positive number. Interesting. So yeah, x is all real numbers. The x-intercept. The x-intercept is where this is equal to 0. And that's going to be 4. Okay. The y-intercept. The y-intercept is what I get when I let x equal 0. When x equals 0, I get -4 to the 2/3 power, okay, which is 2 times the cube root of 2. Okay. Now, since this isn't a rational function, I don't really have any asymptotes. I can tell they're based on the domain, I know that there are no vertical asymptotes, and well, it's not a rational function, so the end behavior is that the function tends to infinity in both directions. So my first derivative is 2/3 x minus 4 to the negative 1/3 power. And that is 0. Ooh, it's actually never 0. It's never 0. However, it is undefined when x is equal to 4. Right? When x is equal to 4, I get the cube root of 0 in the denominator. So I end up dividing by 0. Okay? So this is undefined when x is equal to 4. That means there's something weird going on there. This is my first derivative test. So let's check on either side. If I plug in a 5, what happens? When I plug in a 5, I get some positive number. I get 1, the cube root of 1. I get a positive number. So I'm increasing. When I plug in something less than 4, like 0, I get a negative number in the denominator. And a negative number times a positive number is negative, so I get negative. So now it's an angry anime character, right? Just kidding. That's what that always reminds me of when I see it. Alright, second derivative. The derivative of the first guy, which is going to be negative 2/9 times x minus 4 to the negative 4/3. And that again is undefined when x is 4. Now it's never equal to 0, but it is undefined. It's undefined when x is 4. So the second derivative test will look something like this. We're 4, we're going to plug in 5, and we're going to plug in 0. I like to plug in 0 because 0 is easy to play with. When I plug in 0, I get some negative number in the cube root of a negative number is negative. But then I raise it to the power of 4 and it's positive. But then I multiply by a negative number, and so I get negative. So this is concave down. Now I know that's hard to follow, so let me try again. When I plug in 0, I get a negative number here, negative 4. The cube root of negative 4 is a negative number. I'm not sure what it is, but it's negative. When I raise that to the power of 4, that negative becomes a positive number. And then that positive number, I'm dividing negative 2/9 by that positive number, so I get a negative number, so it's concave down. When I plug in 5, I get a positive number, the cube root of which is positive, and then I raise it to the 4th power, it's positive. And I still have a negative number here, so it's a negative times a positive, which is negative, so I'm concave down. So I'm concave down everywhere, however, I'm decreasing to 4 and increasing from 4. So let's see what this graph might look like. And maybe you already know what it looks like in your head, but there's really only one thing going on at 4, because that's my x-intercept. My y-intercept is 2 cube roots of 2. So we'll call that 2 cube roots of 2. Whatever that is. Okay. So from negative infinity to 4, I'm decreasing, but I'm concave down, and I have to go through that point. Okay. So I look like that. And then from 4 to infinity, I'm increasing. but I'm concave down. So I look like that. So it's kind of like a bird. Kind of like a bird. And if you really think about it, let's go back and think about these, especially this one here. The first derivative is undefined at 4. A vertical line is what has a slope that's undefined. So notice that these tangent lines are getting closer and closer and closer as I approach 4 to being vertical. So that's why that makes sense. If it's undefined, the first derivative is undefined at 4 because the vertical tangent happens at 4.